This is from worksheet number 2, I believe. Yes, the application of exponential equations. So how can we apply some of the things we've learned about exponents and logs? We talked a little bit about inflation in class, and so let's say we have an example. In a developing country, the rate of inflation increase averages 20% per year. That's very high inflation. If the cost of a loaf of bread is $1.50 now, what will the cost of bread be in 1 year? So to find the cost of bread in 1 year, we're going to have to take the original cost of the bread and then add 20% to it. So 20% of 150 would be 0.2 times 150. And if we do this on the calculator, you'll find out this turns out to be $1.80. So in 1 year, the bread has increased 30 cents. Now, what does it mean to increase by 20% per year? Well, it means the next year then I'm going to add 20% to the new cost of the loaf of bread. So we have $1.80 plus 0.2 times $1.80. Now the bread doesn't just go up 30 cents because 20% of $1.50 is 30 cents, but 20% of $1.80 now is more. It's 36 cents. So it goes up to $2.16. And then we can keep going with this. We could say $2.16 plus 0.2 times $2.16. At this point, I can't do this in my head very well. I'm going to have to go to a calculator. But I want to show you also that if we're doing 100% of something, so we have 100%, that's of the cost, plus 20% of the cost, we actually are doing 120% of the cost. So 100% plus this is the 20%. So we're doing 120% of the cost of the bread. In other words, we're going to be multiplying instead of by we're going to be multiplying by 1.2. So instead of saying 1 times 216 plus 0.2 times 216, we can do 1.2 times $2.16. And that will be a more efficient way to find the next cost. Let me show you how this works on the calculator. Our calculator does something called iteration. So if we were, I'm going to kind of move this down so it fits the calculator screen better. So if we put in $1.50 and push enter, and then we just did, if we do control and the little negative sign here, you'll see that it has the word A, it has the letters A, N, S, W above it. It's answer times 1.2. We get that first amount, $1.80. Now, since I wrote answer and it picked up the previous answer, and if I just push enter again, it's going to pick up the previous answer again. 1.8 times 1.2 is 216. Now the third one, 216 times 1.2 is $2.59. 259 times 1.2 is $3.11. So now the loaf of bread costs $3.11 after 1, 2, 3, 4 years of inflation. If I keep pushing enter, this would be 5 years, 6 years, 7 years, 8 years, 9 years, 10 years, and 11 years. So somewhere in between 10 years and 11 years of inflation, the loaf of bread begins to cost $10. So I'm going to write down what I did on the calculator. I did 1.5, enter. Then I did control negative sign, which tells me answer, times 1.5. And then I just keep pushing enter. And when we do that, we found out it was about 10 to 11 years that it took the loaf of bread to first exceed $10. Now, as you might imagine, in math we tend to do things with formulas, so we have a formula that actually will fit this. Notice what we did is we took the original cost of the bread, the 100% plus the interest rate, plus the inflation rate, which was 20%, and we added them together and called them 1.2. And we multiplied that times the cost of the bread. So what we're really doing with this cost of the bread, we're taking $1.50 times 1.2 times 1.2 times 1.2 times 1.2 over and over and over again. If I showed this on the calculator, to get to this same value, we said this was the 11th year, I could do 1.5 times 1.2 to the 11th power, and I get exactly the same number. So I'm taking the initial amount and just multiplying by 1.2 a lot of times, and every time I multiply, it increases the previous answer by 20%. So we can then simplify this equation to y is equal to 1.5 times 1 plus the interest rate to the t power, where t is the number of years, or y equals 1.5 times 1.2 to the t power. And this is an exponential equation because the variable is the exponent. That's why it's called an exponential equation. So I could use this equation to figure out the cost of bread after any number of years. So in this next part here, use your equation to find the year. But for example, if I wanted to find after 8 years, what was the cost of bread, I would just put an 8 in for t. Okay. So let's find the cost of bread. Well, let's also use the equation now to find exactly when the cost of bread exceeds $10. We found it somewhere between 10 and 11 years. So I can say now the cost of the bread after t years is y. So I'm going to say here that y is equal to $10. And I want to find t. So I'm going to say $10 is equal to 1.5 times 1.2 to the t power. The first step in solving this equation is divide both sides by 1.5. Now, 10 divided by 1.5 gives you a decimal number that is a repeating decimal. So if I have something that's a repeating decimal, to keep my accuracy in my equation, I'm just not going to write the decimal. I'm going to leave it in fraction form. Now, how do we solve for t? Students often say, well, could we do like the t root of something on both sides? But that isn't really the method that you want to do, because a root undoes an exponent. So if I know, like, for example, this was 1.2 squared, I could take a square root, or 1.2 cubed, I could take a cube root. But here the exponent is unknown. So when the exponent is unknown, what we do to solve this equation is to use logs. We're going to rewrite this in log form. So we learned, like, here's the base, 1.2, here's the answer, here's the exponent. So we say log base 1.2 of 10 over 1.5 equals t. This allows us to isolate t and find exactly what t equals. So going to your calculator, I'm going to open my log. I can put in base 1.2 of 10 divided by 1.5 and push enter, and there we go. We said that the cost of bread would exceed $10 somewhere between 10 and 11 years. This was 10 years, this was 11 years, so 10.4 exactly. As exact as you can actually get with real life inflation. So we ended up with t is equal to 10.4 years, which does confirm what we figured out earlier just by using iteration. Now the same thing can apply when we do a decrease by a certain percent. So let's say in the same country, because of the high rate of inflation, people are leaving the country. The population is declining at a rate of 5% per year. So if the population is 2 million, and I lose 5% of 2 million, I'm going to be subtracting 5% from that. Well, 5% of 2 million is 100,000, or 100,000. And so if we did, we can just do this on the calculator really quickly. I'm going to go ahead and clear this off and kind of start over. So we have 2 million, 1, 2, 3, 4, 5, 6, minus 0.05 times 2 million. 1, 2, 3, 4, 5, 6, 190,000. Now, if I take that number and subtract, so I'm going to go up and grab this number, enter, and subtract 5% again, minus 0.05, but now I'm taking 5% of 190. Notice I'm just highlighting this and pushing enter and it copies it down. Now I have 1,805,000. So if I calculate the population after 1 year and after 2 years, so this would be 1,900,000 minus 0.05 times 1,900,000 equals what was it? I forgot. 1,805. Okay, so notice it's not going down by as much this time. It's going down by 95,000. Before it went down by 100,000, now it goes down by 95,000. Each time it will continue to decline, but less. So we can use the same type of equation. We start out with our 2 million, only this time we're subtracting. We're taking 100% of what we had minus 5%, and we're going to raise that to the t power. Or we could write this as 200,000, or 2 million times 0.95 to the t power. So notice this base is less than 1. So if it's less than 1, that means we're multiplying continually by a number less than 1. We're going to get a decreasing exponential function this way. So let's use our function to find the population after 8 years. So that means when t is 8. So we don't have to do any solving for this. We just evaluate this on the calculator, 0.95 to the 8th power. So 2 million, 1, 2, 3, 4, 5, 6, times 0.95 to the 8th power. Now, you may be wondering, wait a minute, my calculator isn't giving me these nice long numbers. It's giving me like 1.9 E6 or 1.805 E6. Why are my numbers not the same as your numbers? Well, it may be that your calculator is in a different mode of floating decimal places. Right now, my calculator is in float. So if I were to click somewhere around in this symbol here and go to Document Settings and go to Display Digits, most of you start out with float 6. That means if the decimal number is anything bigger than 6 digits, it will automatically kick it into scientific notation. If you change it to float, okay, and it'll probably say make this default, say yes, then it will display up to 12 decimal places before putting it into scientific notation. Okay, so here's my 1326840.8. So we're going to round that to 1 because we don't want a partial number of people, we want a whole number of people. So 1326841. 1326841. So there's my population. I'm just going to double check that that is right. 268. Yep. So there's the population after 8 years. Now, how many years will it take the population to decline to 1 million? So now I'm saying I want y to equal 1 million, and I want to know what t equals. So I'm going to say 1 million equals 2 million times 0.95 to the t power. The first thing I'll do is divide both sides by 2 million, which gives me 1/2 here, equals 0.95 to the t power. Then I'm going to change it to log form. Log base 0.95 of 1/2 equals t. That will tell me how many years it will take for the population to divide in half. Excuse me. So, log base 0.95 of 1/2 gives me 13.5 years, which isn't very long for a country to lose half of its population. So this is the little equation you can use for both exponential growth and decay right here. You're either adding or subtracting the decimal form of a percentage of increase or decrease. And I'll kind of bring this back down here so you can see this if you didn't have a chance to finish writing that down. In our next video, then we'll apply this to money and talk about the number E.